we propose interactive Robogami, a system that allows casual users to design and fabricate print and fold robots with ground locomotion. The system simplifies the design process by addressing three of its main challenges: the large design space, the interdependence of design subcomponents, and the design fabricability. In a typical robot design process, a designer will address these challenges by first creating a robot geometry and then specifying the movement for that robot. In this linear process, both motion and geometry design are optimized for separately. However, fixing a geometry at a first stage constrains the motion design and may force suboptimal performance. For example, let's look at this robot that a user designed to deliver ice cream. The fastest motion for this topology comes from moving all the legs in parallel. However, using that motion on this design causes the robot to topple over and all the ice cream to spill out. We can change the motion to have the legs on the right move first, allowing the robot to walk forward without toppling. On the other hand, widening the back of the robot makes it stable with the optimal gait, almost doubling the speed compared to the original geometry and drastically reducing the amount of wobbling. Our design tool enables users to explore the combined geometry and motion design space. It tightens the feedback loop between the two stages of the design process, making it more efficient and intuitive. Using our tool, users create a geometry by selecting components from a part library, manipulating the shape parameters, and composing parts together. We have classified parts into bodies, wheels, legs, and peripherals, and have defined a grammar for composition. Similarly, the users design a gait for the robot by selecting gaits from a list of suggestions and modifying the gait parameters. Different gaits provide different trajectories for the robot and can be previewed. In this example, the blue gate makes the robot move forward, and the orange gate makes the robot turn. The designed gaits can be composed together into a gait sequence. The system computes relevant metrics on the design, such as fabrication cost, speed, and trajectory for each gate and the gate sequence. These are updated in real time as users modify the gate or geometry, allowing them to visualize the effect of both design aspects on the robot performance. Users who want to optimize for specific metrics can ask the system for suggestions on how to edit the robot geometry. Arrows in the UI indicate directions of change that will improve the metric. Alternatively, users can select an automatic optimization method that will search for metric improvements in the full geometry space. For fabrication, the system outputs a plan that includes a mesh to send to the 3D printer, a list of electronics and port connections, and software to load onto the microcontroller. Once the user assembles the parts, the resulting robot matches the specification. To evaluate the usability of our system, we introduced our tool to 8 users. The users creatively explored the geometry design tool to produce a variety of wheeled vehicles. An enthusiastic user designed an additional gallery of 18 models using our tool. Users also managed to use the gate design tool and interactive feedback to successfully navigate an obstacle course, taking an ice cream truck to a cake while avoiding fruits and vegetables. Users who were allowed to simultaneously edit geometry and gate designed trajectories that were 40% faster on average than the ones created by users restricted to gate design. We have fabricated 5 additional robots with different geometries and gates. Each of them took about 10 minutes to design, 3 to 7 hours to fabricate, and an hour to assemble. All the robots followed the design gates and walked as predicted by the system. Finally, because the system abstracts away implementation details, users can design robots without specifying the exact fabrication approach. We took a 2-legged, 2-wheel design generated by the system and fabricated it using both our 3D print and fold approach and by folding the pattern out of aluminum sheet. The robot geometries and gates were the same up to a scaling factor. We further instrumented the aluminum robot with 4 range sensors and some additional software that chose a forward or a left or right turning gate based on the sensor information. This allowed the robot to navigate an obstacle course of cardboard boxes and demonstrates the feasibility of building up high-level robot behaviors using the designs produced in our tool.